So hello students, welcome again to my YouTube channel, and in today's video we're going to discuss about the domains theory. So first of all, before we start, we need to know a property about magnets. So let's say for example you have a magnet like this, then this side is the south pole, this side is the north pole. What do you think will happen if you cut this magnet into two? So what normally happens is that, let us draw that diagram. So what normally happens is that this magnet will retain its magnetism even after cutting it into two from this part. Thereby this side becomes the south pole, this side becomes the north pole, this side becomes the north pole, this side becomes the south pole. The same will happen also if you cut this magnet into two like this. If you cut these two magnets into two, the same thing will happen. It will be like this. So this side will become the south pole, this one will become the north pole, this one will become the north pole, here will be south, and then this one will be south, this one will be north, this one will be north, this one will be south. So it doesn't matter how many times you cut the magnet, it will never lose its magnetism. The magnetism will always be retained, and each part of the magnet will retain its polarity. So this domain theory basically it talks about this phenomenon whereby whenever you break a magnet into smaller pieces. So when a bar magnet is broken into two or more pieces, the pieces retain their magnetism, each having a north pole and a south pole at its end. Each having a north pole and south pole at its end. So that is all about domains theory, which basically is just telling you that whenever you break a magnet or whenever you cut a magnet, the magnet will retain its magnetism. Each pole retaining its magnetism, having both north pole and south pole. So if you break it, it will also have a south pole and a north pole. So that is all about domains theory. It basically talks about that. Now we have another thing that is known as the magnetic domains. So magnetic domains, these are basically small magnetic groups. So one common characteristics of this magnetic domain is that they have a common magnetic axis, one being north pole and the other being the south pole. So let's say for example this magnet here, we can break it into some parts, let's say like this. So we can assume that this part here is the magnetic domains. So these are just small magnetic groups. This one is also the magnetic domain. This one is also a magnetic domain. So what happens is that whenever you break this magnet into two, what you basically will do is that you leave part of this magnet. Let's say this side will have its own magnetic domains, and this side will have its own magnetic domains. So and remember we said that one property of these magnetic domains is that they have a common magnetic axis, one being north and other being south. So even if you break this, you haven't destroyed the magnetic domains. So these magnetic domains will still retain their position. Even this one, when you broke it into two, you can just draw a sketch like this. So these magnetic groups will still be retained, whereby this half will still have its magnetic domain and this half will still have its own magnetic domain. So it doesn't matter how many times you break this, at the end of the day each part will still have a magnetic domain which will in turn retain the magnetism of the magnet. So that explains why whenever you break a magnet into half, magnetism is retained in each half that you've just made because of the domains. And we've said that the characteristics of this magnetic domain is that they have a common magnetic axis. So by common it means that it does not change. If you look keenly, this one was the south pole, so this one will still be the south pole and this one will still be the south pole. What will change is the position where you break it. So if you break it here, then you will switch this part to be the north pole, this one will be the north pole, this one will be the north pole. So depending on the position where you cut it, it will switch polarity at that point, because we have said that it has a common magnetic axis whereby one side becomes the north and the other side becomes the south. So another thing we need to discuss about is the dipoles. So what is the dipoles? So what are dipoles? Dipoles basically, in domains, we say that these ones are the domains, these sub magnetic groups, these are the domains. So the dipoles, domains comprises of smaller subatomic magnets. So you can say that this one are, so the dipoles are basically the smaller subatomic magnets, and they're usually found inside the magnetic domains. So we always represent them with lines like this. So you can represent with lines like that. So these lines basically represents the dipoles. So how can we be able to represent magnets and non-magnets or saturated magnets using the dipoles and the domains? So we can draw an example of a magnet here. So we start with A, which is the unmagnetized state. Now how can you be able to represent an unmagnetized state using the magnetic domains and dipoles? So it will look like this. So we can separate this material into magnetic domains. So we said domains, these are smaller magnetic groups. So we separate them like this. And these are the magnetic domains. Later, we need to represent the direction of the dipoles. So if a material is non-magnetized, the dipole will not align in a common direction. So you'll find out that this dipole is facing this direction, another one is facing this direction, another one is just facing this direction. So they're just disorganized. This means that this material has not been magnetized. So this one shows that this material is in an magnetized state. Now let us look at another state. So state B will be magnetized state. So how can you be able to represent a magnetized state? So you can draw a material like this, and then we can break it into magnetic domains. So later on, we can represent the direction of these dipoles. So these ones are the dipoles. So the dipole will align in a common direction, but it will not be in a straight line. All the lines are facing in a common direction, but not parallel to each other. So as you can see, these dipoles are facing in a common direction, but they're not parallel to each other. Now, how can you be able to represent the saturated state? Now, for you to be able to represent the saturated state, let us first draw the material. We can separate the magnetic domains, and then we can indicate the direction of the dipoles. So the dipoles are supposed to be parallel to each other. So they all face in a common direction and are parallel to each other. So we normally say that the material is magnetically saturated. This means that all the domains get aligned in a specific direction and are parallel to each other. No further magnetism or magnetization can take place. This is the final stage of magnetism.